My name is Uri, and I work at Certora. It's a Web3 security company that had built a few public goods in the space. And today, I'm going to talk to you about a $5 million bug that no one caught in time, why it will be challenging to catch it with fuzzing, and why it will be pretty difficult to catch it with formal verification too. And then I'll present a different idea called bounded model checking. We'll talk about what it is and how it works. And by the end, we will know another tool that we can use in our arsenal. On March 6th, around 4 months ago, $5 million were stolen from 1inch, which, if you don't know, is a decentralized exchange. The vulnerability was live on mainnet for 2 years, and it was missed by 9 different audit rounds. The vulnerability lied in the function settle order. This function received a structured call data input and moved it over to resolvers. It handles swaps in 1inch. Part of the expected buffer had a section called the interaction, and that interaction had a declared length. The attacker exploited this function by, first of all, creating a normal swap, except he traded pennies for millions. And the way he did it was by giving it a bad length, a negative length of minus 512. That caused the memory pointer to underflow. And unfortunately, we were inside an assembly block, so no underflow guards were present. And the attacker could put whichever data he wants inside the interaction section. So that means that he bypassed all access controls and could do whichever fund transfers he wants. So why did it miss so many audit rounds, including some of the most well-known auditors in the space? Right. The first reason was that the function was deprecated and thought to be unreachable. So it seems very likely that the auditors didn't spend that much energy on it, as they did in other parts of the code. It was also low-level code. It was YUL, so it's harder for us humans to read it, reason about it. And also it required a very specific input, especially the number minus 512. So it's clear that sometimes human auditors can't catch all the bugs. And that's why we strive to use as many automated tools and not automated tools as we can to increase the security of smart contracts. And one of the first tools that we can use is fuzzing. So fuzzing, if you don't know, is the process where the computer generates a lot of different inputs, hammers them all into the test. It's some sort of a brute force approach. And we try to see if one of those randomly generated inputs will cause a failure. Let's delve a bit deeper. So here I'm going to show you some code examples from Lido. Lido use Foundry, so the code here is in Solidity, more or less. Every fuzz test starts with a setup function that kind of initiates the world for us. So it will call the constructors, it will set up a few different accounts, it will give some access controls, and the idea is that we want to start from a state that is interesting, that something could be stolen, something could go wrong, right? If there are no accounts in the system, then that's not very interesting and doesn't really represent how it will work like in the real world. And after that, a test will usually look like that. We have some assertions, which are conditions, and we have some function calls in between. And the important thing is that the parameters of these tests will be randomly generated by the computer. So here we have 2 different inputs, right? We have the number here, the data, and we have the bytes, the position. So the computer will try to generate many, many, many different inputs. I'm talking about hundreds of thousands, millions, the more the merrier. Fuzz testing, however, is a bit limited in what it can do. If we want to find an exploit, we need to get the right condition with the right functions before it, which is sometimes something that's very hard to do. For example, in 1inch's case, we thought that the function was unreachable, so maybe no one would even write a test like this. And that's why we have other tools that are doing something called invariant testing. An invariant of a smart contract or software in general is something that should always hold true. And if it doesn't, it means that we're in trouble. For example, for a decentralized exchange, one of the invariants we can say is that an account should not lose funds due to another account's actions. What does that mean? If I have an account in 1inch, then I may lose funds, I may lose some money due to market conditions, the token went down. But I shouldn't lose money if Bob decided to swap, right? That's not related to me. And there are actually tools that can try and see if the contract behaves according to this invariant. And today we're going to talk about 3 of them. We're going to talk about invariant fuzz testing, formal verification, and bounded model checking. Invariant fuzz testing is the next level of fuzzing in many ways. Again, we start from the same set of function like the one we saw before, except now instead of calling one specific function, we're calling a random external function in the contract. And like previously with fuzzing, the inputs are also randomly generated, and is also sent by a random address. And after calling this function with the random inputs from the random address, we check if the invariant still holds. And if it does, we just do it again. We call another random external function and check it again, and so on. We usually do it for 15, 20 times. That's the usual amount. And if it all passed, we start all over. We go back to the sub function. We call again random functions with random inputs and check and run and check. And we continue to do that for many, many call sequences. Again, we want to run hundreds of thousands. So this is already a step up from fuzzing, because we now call all the functions, right? We don't call a specific function before we check our test. But still, the input coverage of fuzzing is relatively low. For example, in the bug that I've explained before for 1inch, to get to the exploit, the call data has to have the correct layout. Otherwise, the function will revert and will not see the exploit. So not only does it need to have the right structure, it also needs to have the correct length of -512. And the chance to stumble upon all that if we just randomly generate numbers is slim. There is another issue with invariant fuzz testing, and that is program state coverage. A program state is the content of all the storage that includes, right, about the funds, the accounts, the access controls, everything that we can say about the world. That's the state. And obviously, a lot of exploits require some specific states. There are practically infinite states for a program. There are a lot of different options of a program state. And in fuzzing, invariant fuzz testing, we cover some of them, right? We always start from the same initial state, the one that the setup function defined for us. And then whenever we call a function, unless it's a view function, we reach a different state. And then whenever we do another step, we reach another state. So the number of states that we explore grows linearly with time, which is nice compared to regular fuzzing, but it's a drop in the ocean compared to the number of infinite states out there. So that's why we sometimes want to go to a different tool. For example, formal verification. Formal verification tries a different approach. We're not trying to randomly generate inputs. We're trying to prove things about the system mathematically. How does it work? In general, we get 2 different inputs. One is the code that we try to secure, and one is something we call a specification. It's basically the test that has the invariant that you're trying to test. We put them both together to the software which compiles them to a mathematical logical formula and tries to prove it. If we get a proof, then the proof always holds. It's like a theorem in mathematics. We don't actually have to try all the different values of x to say something with a theorem about a number x. And we do the same here. That's why we can do that. We cheat. We use math. However, if we can't prove, many times we find a bug. So when we see that the theorem doesn't hold, the tool will tell us it doesn't hold when I call this function with these inputs starting from this state. So that's great. And let's look into a little more details. How we check invariance with formal verification? We start from an arbitrary state, which is not the same as the initial state we had before, and it's not randomly generated. What it means is that we give the prover the freedom to choose the inputs that will cause a violation. And that means that it will think like an adversary and try to give inputs that will cause a failure of the invariant. And then we're going to call the external functions, all the external functions in the contract, except now, instead of trying to randomly generate the inputs, we're going to use symbols, like x in a math equation. So it can take any value. And again, we use math at the end, so that's totally fine. It's not going to run. Again, from a random address. And then we go on, and we started from an arbitrary state. And at the end here, it's not an arbitrary state, but it's a class of states that are symbolic states. All the states that I can reach from one step by calling the deposit function. I do that for all the external functions in the contract, and if I get a proof for all of them, then I've actually covered all the starting states, all the inputs. It's perfect. Except now we have the opposite problem. We've actually covered too many starting states. So what we care about is not actually all the mathematically theoretical possible states of a contract. We care only about those that you can actually reach by running the program and calling its functions. So a fuzzing cannot cover all the reachable states, but formal verification covers some states that are actually not at all reachable. And that means that they're not interesting. For example, if we will try to prove the invariant I said before, that an account should not lose money due to another account's actions, one of the counterexamples I can get is that there are just too many tokens. I'm swapping tokens, and then it overflows, which doesn't make sense. But the prover doesn't know that the amount of tokens has to be smaller than, say, the total supply. So it will give me that example. It had the freedom to choose it. And I need to tell the tool, don't do that. So I constrained it. Let's say I did that. I run the tool again. Now I have a counterexample due to wrong internal accounting. And that means that the variables inside the contract of the exchange do not correctly represent its assets. So I can assume that it does, right? And continue going on. But is it safe to do so? If I assume that the internal accounting is always right, I'm going to miss bugs, right? Potentially. So now I actually need to try and prove that, like proving a lemma before a theorem. And now I'm a bit in a rabbit hole and trying to prove more and more things before I'm proving the thing I care about. And that's where bounded model checking comes in. Bounded model checking is an idea that we start from a specific initial state, like we did before in fuzzing. And now we call, again, all the external functions of the contract with symbolic inputs. Now I reach two different states. Again, not a single state. It's a symbolic state. It represents all the states that I can get to by one step of calling that function. And I do it again. So that means that whenever, for each state that I go to by one function call, now I call another function call. And I do that again and again until I reach a certain depth of function call sequences. So I'll briefly go into some technical details. How would a call sequence look like? At first, I'll zero out the entire state. Then I call all the constructors. If they have inputs, they will be symbolic. Call the setup function like I do in invariant fuzz testing. I call 4 external functions of the contract with arbitrary inputs, could be anything. and then I test the invariant. And I will have a sequence for every combination of 4 external functions in the contract. Another analogy to understand it is that fuzzing goes deep. It's like DFS. I'm going straight ahead, going 15 functions deep, then starting all over again. That's not how bounded model checking works. Bounded model checking first checks all the states that I can reach with 1 step, then all the states that I can reach with 2 steps, and so on and so forth. Bounded model checking has been used in the industry for many years, but not yet in Web3 to our knowledge. And it has been used in many different fields. It has been used to verify C programs by Amazon. It's still being used. NASA developed a tool to do bounded model checking for Java programs, and it's used all over the place for hardware by Intel, NVIDIA, and so on. So it's not a new idea, but it's a new application. And unfortunately, it also has its own drawbacks. So the amount of different call sequences grows exponentially as we increase the depth, because every time we have a choice of all the different external functions of the contract. So it's exponential growth. That means it doesn't really scale all that well. And that means that in future research, we will try to focus on choosing paths that are more likely to lead to an exploit. And that also means that we will try to ignore paths that we have maybe already covered, or we think there is a very low chance of them leading to an exploit. So finally, let's compare all the 3 different technologies. First of all, we have input coverage. So for fuzzing, we saw it's pretty low. However, we use symbols, so formalification and bounded model checking have perfect coverage. The state coverage of fuzzing is low, as we saw before. It's perfect for formalification because we started from the arbitrary state. And bounded model checking is somewhere in the middle. So we deal with symbolic states, right? We call these functions with symbolic inputs. However, some states we will not find from the initial state, maybe at all, maybe not in the end steps that we have checked. So we don't cover everything anymore, but we cover a whole lot more. So it's something in the middle. However, one of the advantages of bounded model checking is that now all the alarms it gives make sense. So we no longer run into the problem of unreachable states. Whenever we see a violation of the invariant, we know where exactly we've started, which functions did we took, which state did we pass through, and it's all diagnosable. So I hope that today you've learned that we can use tools to increase the security of smart contracts. We can use fuzzing, but it cannot take everything, find everything. We can use formalification, but it's hard and it's effort intensive. And we can use bounded model checking as a middle way between the two. If you're interested, you can see our code in the GitHub here by scanning it. It's open source. Thank you.
Thanks, guys, and that's all the time we have for today. Thanks. We can ask some questions here.